Well, today I would like to try something new. I'm going to use my new toy as a whiteboard so that I can share my lecture notes easier with you. Yes, that was over the end of the semester, but şuradan ses çıkıyor değil mi? Tamam. Well, let's start. So today we are going to do superconductivity. Well, it feels extremely awkward to me because I'm so used to writing it on the board. Okay, before we start, again, as a friendly reminder, this Friday we are going to have our second midterm at 1740 here. Okay. All right. So let's wait a few more minutes before we do the quiz that I promised you last time. It is necessary. Actually, this is beneficial for you because the lower number of quizzes I make, the higher score each quiz is going to have. So if you missed a quiz or two, or if you did badly on one quiz or so, then its weight is going to be higher in your grade, if that's your major concern. Okay. All right. Well. So, well, still, its weight is going to be less. So this is really good for you. Okay. So let's start with superconductivity and wait for a few more people to come in. Well, I think no. Let's do it now. We already have everyone. Because I was going to do it in the previous lecture actually. So this is like continuation of the previous lecture. It's just one very simple. Okay, so as promised before, we will be doing superconductivity today. Now, in many metals, if you measure resistance versus or resistivity versus temperature, the graph you will get is going to be something like this. As the temperature goes down and down and down, at very low temperatures, the resistivity, so this is the resistivity, and this is the temperature. At sufficiently low enough temperatures, the resistivity will reach a plateau, and so this is a metallic sample, okay? Under normal circumstances, you would expect the conductivity, sorry, the resistivity in a metal to reach 0, okay? That follows the linear trend at relatively high temperatures. You can see it, right? It's readable. What's that? Sure. So I can write larger. Okay, well, it doesn't allow me to go any smaller than that. And this residual resistivity stems from the fact that you have inevitable impurities in metals. So there are many scattering centers at low temperatures that results in a residual resistivity. Yes, I'll share. That's why I switched to this. So, well, it's up to you. I mean, it's totally up to you. Okay. Yeah, sure. So I'll share these notes. And this is what you get for many metals like copper, gold, silver, and some other metals as well. Actually, I can cheat from the book to cite some other metals. So, especially magnetic metals like iron, and then like manganese, cobalt, nickel, and so on. They don't show superconductivity. So they show this behavior. I'll come to superconductivity in a moment. So in other metals, this is what we observe. So we observe the same linear trend. Of course, the resistivity doesn't have to be the same, but you got the idea. I mean, it can be a very different curve. You know, the slope can be very different, but that's not the point here. What happens is that once you reach a certain temperature, some critical temperature, resistivity becomes 0. And this is not just a small resistivity. It is truly 0 resistivity. Okay? So in some other metals, the easiest one is niobium. Then vanadium shows superconductivity. Actually, pretty much half of the periodic table shows superconductivity. Some metals at much lower temperatures, like the typical TCs are like for niobium, it's about 9.5 Kelvin. For vanadium, it's 5.38 Kelvin. And there are some others like molybdenum. It's 0.92 Kelvin. Yes? It's completely 0. Not even like a tiny amount. It's completely 0. Well, actually, we are going to do a rough calculation of that estimation. Using the model that we use, it turns out that the lifetime is about 10 to the power of 10 to the 7. So it's much, much larger than the age of the universe. That's a theoretical prediction. There are some other models, as you suggested. The current can persist for hundreds of thousands of years. And then we will also see In some types of superconductors, very close to the critical temperature, there's a very small residual resistance remaining, but we know the reason for that as well. So when you lower the temperature sufficiently enough, that resistance, that residual resistance also disappears. So to our best understanding, there is no resistance at all in superconducting materials. So that's the first thing that's we should note about. That's the first apparent property of superconductors. Okay, so I can list many other examples. Like in the case of tungsten, that's I guess the most extreme case. Or I'm not sure if there are other extreme cases, but the superconducting temperature is only 12 millikelvin. Okay, so it's extremely low. But still, we do observe superconductivity in this material. And I'm not sure about the most recent studies, but the highest observed temperature, superconducting temperature, is I think around 250 Kelvin in H2SE compressed to 90 gigapascals. So the pressure is extreme. H2S is actually a gas at room temperature. I cannot remember its freezing point, but so the temperature that it becomes a liquid. But I think it's pretty low. So they compress it to a point, it solidifies, and then when they measure, this is the record high superconductivity that has been ever achieved. But in a sense, it's useless because these such high pressures are not practical. We have much better materials, actually. YbCO. I need to be able to write down the exact formula. I need to cheat. It is yttrium, barium, copper oxide, and this is 6.9. And the transition temperature is 90 Kelvin, and that's already a very nice number because the temperature is above the temperature of liquid nitrogen. So at 77 Kelvin, liquid nitrogen starts boiling, and nitrogen is extremely abundant. It's very easy to liquefy. We have a huge tank sitting just outside of the UNAM building. Yes.
Where do they use it?
In all sorts. I mean, we use it in all sorts of experiments. It's easier to transport it that way. So it comes in a tanker. We fill that tank, and then it supplies nitrogen to the clean room because it evaporates, and we use that pressurized evaporated gas to supply nitrogen to many of the equipment. And then downstairs inside TEM, you constantly need to put liquid nitrogen to the detectors so that it can stay relatively noise-free. And then again downstairs in FIB, if you really want to do precise cutting or deposition, then you need to cool down the whole chamber so that there won't be any outgassing coming from the chamber. We pour liquid nitrogen. What else? What's that? Yes. So yeah, pretty much. There are many instruments that we use liquid nitrogen for, and in biology they prepare samples. I guess somehow they freeze them and then they take slices from the frozen samples and so on. So there's many uses. It's very easily accessible refrigerant. Sometimes we use it for our experiments. We put it in a dewar and then we pour it through some channels to cool down our samples. So yeah, it's very easily accessible. And this transition temperature, superconducting transition temperature, is already above 77 Kelvin. So this material was a huge success. I think its discovery was sometime around 1986. So they accidentally discovered this material. And till that date, the highest superconducting temperature was something like 30 Kelvin. And that was a huge, huge impact on the society. All of a sudden, people started mixing different materials to obtain higher and higher superconducting temperatures, but with little success. So this is probably the most abundant superconductor that we have today, that is commonly used in many applications, and it's easy to produce and so on. Okay, so okay, what else? Now, one property that we talked about is the zero resistivity of the materials. Another one is called the Meissner effect. And the idea is that the magnetic field, this color, magnetic field is completely expelled out of the material. So, in a normal dielectric material, when you apply a magnetic field to the material, magnetic field lines will penetrate into material and pass through the material. Okay? Of course, we are talking about moderate magnetic fields here. By moderate, I mean magnetic fields not greater than 1 Tesla. Sorry, I should write B here. Okay? Even in certain cases, 1 Tesla is too large, but let's say we are talking about 1 Tesla. As soon as you go below TC, in some types of superconductors, this is what happens. The magnetic field lines will be repelled, so they cannot penetrate into the material. So that's wrong. Okay? So this effect is called Meissner effect, and this is not the case for all superconductors, as we'll see. We will do a classification of superconductors depending on various factors, but in some superconductors this is the case. And probably you have seen examples of this in, I don't know, actually I can show you a video regarding magnetic, it's trying to understand it in Turkish. Let me switch to keyboard. So let me show you this. Probably you have already seen this, but it would be magnetic levitation. All right, I don't have internet connection, so you're gonna trust me. I'll just describe what it is. Let me see if I can connect. Okay. Let's see. All right. I hope this.
Magnets can be created by running currents through wires, by finding a suitable material. One more kind of magnet.
Well, the idea is, let's see. No, sorry.
An external magnetic field causes the electrons.
It's just talking about general magnetic levitation.
Motion generates an opposing
So,
magnetic field. This field is pretty weak, but it does cause the material to be repulsed from the magnet a little bit. For example, if you hang a wooden toothpick in a magnetic
Let's see, which one has the higher views and shorter. I don't want to wait too long. Okay. So he wraps the superconductor, so they cool it with liquid nitrogen and place it over magnets, and voila, it's levitating in mid-air. So they're using some sort of quadruple arrangement. So in a way, the disk is locked in place. Okay. So that's something you can do with magnetic levitation. A more interesting demonstration is that you place the normal superconducting material in its normal state over a magnet. So it just rests there, and then you start pouring liquid nitrogen. As soon as it reaches the superconducting temperature, it starts floating up in the air. And the reason that this expelling of the magnetic field forms a stable configuration for this material, so it sort of floats. It can overcome its weight, and it stays very stable. And indeed, this is not just for scientific demonstrations. Probably you have heard maglev, the trains that can travel at insane speeds, and they use the exact same principle. So they have superconducting magnets on the train, and then they have these magnetic rails. So they have sections of electromagnets over the rails, okay? And then the train has the superconducting magnets, and then of course it has its refrigerators and so on. And as soon as it cools down the superconducting material, the train starts floating, and then by alternating the polarity of the magnets and only powering the relevant sections on the track, they can accelerate this train. Since it doesn't carry any motors or anything, it's a very lightweight train, and it can travel at speeds up to, I don't know, 500 kilometers per hour. And there's only air resistance. There is no resistance coming from the tracks. It's literally flying over the tracks. So, yeah.
The tracks in this type of
Mm-hmm.
train is different from usual trains.
Yeah, it's extremely different. It has nothing to do with usual tracks, actually. These tracks.
What's the material they use?
So it's not a conventional track, actually. It doesn't rest on rails. There's only one giant column that goes in between the train. So again, I could find the pictures, or you can Google it by yourself. And within this center track, there are segments of electromagnets. And what they do is they power these electromagnets in a sequence, and that sequence pushes the train. So the train can accelerate, or they can reverse the polarity, and then they can slow down the train. So in a way, it saves energy because you only power certain sections of the track at a time. And also the train makes no physical contact to the rails, or there are no rails actually. It just floats in the air. Mm-hmm.
How they can slow down the acceleration of the...
So it's just reversing the polarity of the magnets. I'm not sure about the technical details, or I cannot at the moment wrap my around how actually you need to power these in sequence so that it will create a forward flow or slow down the train. But as far as I know, what you have to do is you need to somehow arrange these segments of electromagnets in such a way that it can create a direction to the motion. Again, also there are some videos online that shows how. Let me see. There actually I have seen one. Yeah. So this is a mock-up version of that train. So there are magnetic segments. Let's see. Of course, these are not electromagnets. They are fixed. So as soon as he places, let's see. So he cools down. It's in liquid nitrogen. You see the video, right? As soon as it cools down, it starts levitating. No, okay, the arrangement is not, I think. Yeah, so. Well, anyways, there is a certain arrangement that you can make to accelerate the train in a certain direction. But that's just a side note. I mean,
Can you explain what is the force that neutralizes the gravity?
okay, so the idea is this. Now, once we apply the magnetic field, let's do it this way. Now, I have the gravity, obviously, and then in its normal state, let me use this one, I have magnetic fields. That's a static magnetic field and has no effect on the motion of my electrons. Now, as soon as I start cooling the material, what happens is now I have electrons inside the material. Perhaps let's do it this way. I need to explain a few more concepts to be able to explain the generation of the force. Let's finish this section because I need to introduce a few more concepts, and then I'll explain, because I need to explain the Cooper pairs and then how they react to the diminishing magnetic field and how it creates certain currents within the material that counteracts the magnetic field. So let me introduce them first and then I'll explain that question. Okay, so any other questions? Okay, let's continue with properties and classification of superconductors. Okay. So now the first classification that we can make is we say type 1. Okay. So in the case of type 1, there is a critical magnetic field let's define as BC that destroys superconductivity. So to a superconductor, if you apply a large magnetic field, then you destroy the superconducting order. And we'll explain why this is so. This is if there is a critical field. So if you can draw this, let's say this is resistivity versus magnetic field. If you can draw something like this, or I don't know, this can be a flat line as well. It really doesn't matter. So at certain critical magnetic field, resistivity all of a sudden makes a sudden jump. then this is a type 1 superconductor. In the case of type 2, there is a range of magnetic field that gradually destroys the superconducting order. Okay, so what happens is that there is, again, we can draw the same graph. You have zero conductivity, and then for a range of magnetic field, there is a residual resistance or resistivity in the sample, and then the superconducting order is destroyed. And these are called type 2 superconductors. Then this is one way of classification, if you like, type 1 and type 2. So this is with respect to the effect of magnetic field. Then another classification that we can make is conventional and unconventional. And in the case of conventional superconductivity, it can be explained by a theory that we will see in a moment called BCS theory. And then in the case of unconventional, it cannot be explained by the BCS theory. Okay? Then another classification, so this is regarding the theory that we can apply to. Another classification that we can make is regarding the temperature of the phase transition, superconducting transition. We call typically them high TC superconductors if the transition temperature is about 77 Kelvin, so liquid nitrogen temperature is the criteria there. Then we call them low TC if it is way below 77 Kelvin. So that's another classification. And incidentally, all high TC superconductors are unconventional, as well as they fall into the category of type 2. So that's probably not a coincidence, but that's something that people typically confuse, or use interchangeably when they say type 2. They mean high TC or unconventional superconductivity, and vice versa. But this is the actual classification. And there are instances, for instance, there might be some type 2 superconductors that can be that can have low temperature of transition. Okay, so now let's try to understand the theory, this BCS theory, and then this will give us an idea about how we end up with superconductivity. Okay, so let's start discussing the BCS theory. So the name comes from these three physicists, Bardeen, Cooper, and Schrieffer, and they have this 1957 paper that they explain the superconductivity. And the discovery of superconductivity dates back to 1911 by Kamerlingh Onnes, or something like that. And this guy is actually a guy who tries to liquefy helium, and then he succeeds, like in 1908, he gets liquid helium. So he's basically a guy that works on low temperature or how to achieve low temperatures in those days. And then, I mean, the most obvious thing is when you cool down things, you know, freeze liquid mercury and try to measure its properties, because otherwise dealing with mercury is rather difficult. It's difficult to measure its properties. And then his student tells him that I read zero resistivity or zero resistance from the measurement. And then he gets really angry because he thinks that his student is making a stupid mistake because it would be impossible. He checks the cabling, he repeats the experiment himself, and he really sees that there is no resistance to the flow. And then that dates the discovery of superconductivity in solid mercury. And then he starts looking at other materials, and he realizes that this is not something that's only applicable to mercury, but there are many other metals that show the same property. So, and then people struggle to understand why this might be the case, why all of a sudden materials show this amazing property. And then in 1957, these three gentlemen explain one side story regarding this guy. This is the only guy who got 2 physics Nobel Prizes. So one is the discovery of transistor, and the other is discovery of superconductivity. So it's not a commonly known name, but he literally changed the world. So, and there's also this story. I really enjoy that story. When he got his first Nobel Prize, the king chides him and says, "Why didn't you bring your kids and your family to the ceremony?" And he says, "Okay, I'll bring them next time." And he keeps his promise. So, I really enjoy that story. I mean, he's so confident that he's going to get it for a second time, and he keeps his promise. So the theory is as following. Now, the first observation that we should make is that there is an attractive interaction, between electrons can lead to a ground state separated from excited states by an energy gap. So I copied this expression from this book, and so the idea here is that somehow 2 electrons start attracting each other. I mean, under normal circumstances, this is something you wouldn't expect, because there's Coulomb repulsion that repels each electron, okay? So the idea is that if these electrons can have an attractive interaction among them, then there can be a new ground state that has a lower energy than the other energies of the electrons in the system. Then another thing, so how to achieve this, is that actually electron lattice interaction leads to an energy gap at the observed magnitude. So the idea is this. At sufficiently low enough temperatures, let me draw, so these are my ion cores, okay? So this is the crystal. Let me draw a few more atoms. And these are electrons. At sufficiently low enough temperatures, now the wiggling or jiggling motion of these ion cores are relatively suppressed. So what happens is that the interaction between the electron and the neighboring lattice becomes more significant than the thermal smearing or thermal motion of the atoms themselves. Which means this electron can shift these ion cores as it travels through the material. So it's a local shift. So it slightly attracts these ion cores because remember they're positively charged, and the thermal motion is now no longer in consideration. So the average displacement is something that electron can manage. So the atoms don't go back and forth, and also the electron itself has a relatively well-defined energy. So it creates a local distortion in the lattice, which the net effect is to minimize the local energy of this configuration. But then, all of a sudden, you form an lower energy state, and then this electron is attracted towards that lower energy state. So the separation can be as large as hundreds of nanometers, but still it feels that local distortion. And then this electron will be attracted, and they sort of start moving together in the presence of these two local distortions that are created by these electrons. So the pair, so it's attracted to this electron, and now if I move this electron to a next unit cell in the crystal, this electron will follow it because now they can be described by the same potential minimum. Okay? So all of a sudden they start acting together. And this is the attractive force between the electrons. One electron distorts the crystal, another electron sees that distortion, or both distortions, when they combine together, forms a new potential minimum. And then these potential minimum is protected since we are at low temperatures, and these electrons start moving together. Now, when you have, of course, this is a very simplified picture, but to be able to for these electrons to be in the same potential minimum, or to form this ground state, one is in spin up, the other is in spin down configuration. Okay, so the net, we call this quasi-particle. So it's like a particle. It's not really a particle, but since it moves together, we can treat it as a single particle. And this quasi-particle, because of the spin configuration, and it tries to achieve the lower energy state, forms a boson. And if you remember from the very first lectures, we had two types of particles in terms of the statistical behavior that they follow. Fermions, they had half integer spin, and electrons are actually fermions, or protons or neutrons, they are fermions. So they cannot occupy the same quantum state. But bosons, like photon itself, or in this case the Cooper pairs, these pairs are called the Cooper pairs, they form a boson and they can occupy the same quantum state. Now imagine a crystal that contains 10 to the 23 such bosons that they can occupy the lowest energy state without interfering with each other. So this means all of a sudden these electrons reach a ground state energy. Now, this explanation actually sort of tells us now why we have these electrons. They can travel without any resistance because they are bosons, and in a way they form a superfluid, and there are certain quantities that are associated with it, like coherence length, and this coherence length, as I mentioned before, can be on the order of hundreds of nanometers. So to be able to scatter these electrons from impurities, any interaction that needs to be comparable, or range of that interaction needs to be comparable to the coherence length. Otherwise, you cannot destroy this quantum state that these electrons are in. So the scattering events are exponentially suppressed. Okay? I know I spoke a little bit in too much jargon, but the idea is that it's very difficult to destroy these states via scattering events, because the scattering events are exponentially suppressed because of their ranges, and the coherence length of these electrons are quite large. And indeed, one way to destroy superconductivity in a material is to put magnetic scatterers, so that, for instance, if you start replacing niobium atoms with iron atoms in a niobium crystal, then these magnetic impurities will act as scattering centers. So before niobium can actually, these Cooper pairs can form, the spins will start scattering from these magnetic impurities, and it will destroy the formation of Cooper pairs. So that's one way to look at it. It is related to Kondo effect, but I wouldn't say Kondo effect. So let's give a 10-minute break, and then I'll come back to your question, okay? Because now we have all preliminaries. Alo. Evet. Geliyorum. What's that? Mm-hmm. Well, actually, it's not affected by disorders that are non-magnetic. Yeah, that's very critical, because if you I'm not sure. I'm not sure if you can describe it as a topological order. Do you have any ideas? Mm-hmm. Mm-hmm. I'm really not sure. Mm-hmm. Yeah. Mm-hmm. Yeah, because the range of interaction can go, as I said, up to like hundreds of nanometers, and yeah. Yeah, no, this is they are not localized. I don't think we can say weak localization. Because still the electrons are actually not localized. It's just a local distortion, and it's not even weak localization. So it's just yeah, I don't think so. Okay. Yes, sure. Well, that's, I guess, a question that no one can answer, because we are talking about pretty identical objects, and we are talking about a mass of electrons. Like it's really, electrons are everywhere. But once they form the pairs, still two pairs will be indistinguishable, because they are really identical quasi-particles now. So
when they compare, this pair not break and another pair.
Wow, I don't know. I don't know that question. But I wouldn't expect them to break, because then they're in the ground state, and to be able to break a pair, there is a certain energy that you need to provide to these electrons. So actually this energy gap, I'll explain what I mean by that, the energy gap. But that's the energy gap, that's the energy that's required to break apart these electrons. So unless you can provide that energy to the electrons, real breaking, so an event that will take a certain amount of time is probably unlikely. But then, I don't know, there might be some exchange interactions. Yeah. Yeah. So
they are in the ground state. There is no way that another electron can play and make the energy lower.
no, they're already in the ground state of the system.
And another question is that's temperature. Approximately how far are they scattering, for example, moles or something like that? Is it possible one of them
So, yes, that's possible. And let me see if I can give you any numbers regarding the scattering length. I cannot see any numbers, and I don't know any numbers on top of my head, but okay, there's this intrinsic coherence length in table 5. So the coherence length is, for the case of aluminium, for instance, it is 100, or I should say 1.6 microns. So, but I'm not sure if impurities, but then again, the disorder in the system and the magnetic impurities should destroy this. So I'm really not sure about the answer to that question. Okay. Any other questions that I cannot answer? Okay.
What are these magnetic impurities?
Like cobalt, iron. So,
Introduce these impurities.
well, they're inevitably there. Any process, any purification process will leave some impurities in the system. And no matter what you do, they will be there. And the ratios that we are talking about, actually, I've noted it down, is not like too high ratios, even in like 1 in 1 million or 1 billion is enough to destroy the superconducting order. So if you have like few iron atoms in a niobium crystal, that's enough to change the magnetic, the transition temperature. And as you increase the number of impurities, the transition temperature decreases gradually, and at some point it reaches to 0. So let me see if I can find, there was a graph that shows the superconducting temperature versus the amount of impurities. Let me see if I can find it. I prepare these lecture notes from many different books and sources, so I see something in some place, I note it down, but then I don't write down the reference, so I lose track of where I've seen it. So probably it wasn't in the book. But anyways, a small number of magnetic impurities is capable of destroying this magnetic order. Okay, any other questions? Now, before answering the mechanism behind magnetic levitation, there is one more thing that I would like to introduce. So it is called, let me use this, London penetration length. So in a superconducting material, as we mentioned, the magnetic field cannot enter into the material. So when you apply a magnetic field, let's say again I have, I don't know, some north pole here and a south pole there. So I have magnetic field lines coming out of this. So this material, the superconducting material, acts as a perfect diamagnet. So what happens, of course, at the microscopic level is some of the magnetic field lines actually penetrate into the material. And that penetration is due to several reasons. One of them is, again, impurities and defects. So certain scattering centers. And because of this reason, this small penetration of magnetic field into the material, now you still have your Cooper pairs that are around here. You start forming currents that are persistent. Okay, so as soon as it enters into the superconducting regime, now you have superconducting currents that are flowing within the material. So that's one reason that we can pinpoint. And then another reason is that there are some of the magnetic field lines actually, although very weakly, will follow certain defects and pass through the material. But this is very a rare event. So the net effect is, so let's say when you have a magnet underneath your superconducting material, because of the formation of the eddy currents and also this leaking magnetic fields within the crystal, what you end up with is a force that, or a magnetic field that has the same and opposing magnitude as the original magnetic field that opposes this force. Also, this is pretty much locked in place. It's not unlike two magnets facing down on each other. The reason being is that this London penetration depth, so lambda L, is invariant of course, as you change the strength of the magnetic field, the number of eddy current or the strength of the eddy currents that you create will differ. But considering that we have somewhat uniform magnetic field, will give roughly the same amount of currents, and this will create a stable configuration. And also these leaking magnetic fields will help pinning the levitating object over the magnetic field. So now let's try to, I don't want to go into details of the equations, but the idea is, perhaps I should write very briefly. So the current density, so it's a vector, of course, so I'm going to write it in terms of a vector potential, A, and under normal circumstances in free space, this is what we would have, okay? Of course, it depends on the gauge you choose, but in some gauge we can make it to look like this. But in a superconductor, this penetrated magnetic field will have this extra term, and this extra term, lambda L squared, is the penetration length. Okay? So if you solve the equations, now curl of B would be mu 0 J, okay? And if we take curl of B, then after some algebra, this is what I get, is mu 0 curl of J, and this leads to this equation, lambda squared B, this is the vector, B over lambda L squared. And this gives us a decaying solution. What I have written here is valid for within the material, okay? And if you solve for this differential equation, you get an exponentially decaying function. So this B of x, if we assume that this is my x coordinate and this is the superconductor, is something like B0, magnetic field at the surface, e to the minus x divided by lambda L. And this lambda L, if you solve for it, turns out something like epsilon 0 mc squared divided by n q squared square root. Okay, so this is how far magnetic field lines can penetrate into the material. And indeed, the distance depth. Indeed, that distance, for instance, for the case of aluminium, it's what is it? It's 0.16 nanometers. It's extremely short. So it's about less than a unit cell. So it's really confined on the surface. And of course, there are much longer ones and shorter ones and so on. So this is the case for aluminium. Okay. So any questions? Okay. Now, how do we measure? Let me switch back to red. How to measure zero electrical resistance? Does anyone know how people measure these superconducting materials? Because think about it. But now let's consider this. I have a superconducting sample, okay? And then let me use different colors. And then I need to use some sort of instrument that's not superconducting, right? My voltmeter is not a superconducting voltmeter. So I must have normal leads. So this will be a normal conductor, this will be a normal conductor. So if I apply a bias and then hook up a voltmeter here, what will I measure? What I'll measure is the current that runs through here. There will be some current that will be injected into superconductor because I have wires here that are normal conductors. I have wires here that are normal conductors. So there will be some resistance. And then I have some wires here and then some circuitry inside that has some resistance. So the current that runs through this superconducting material is going to be this, but still, how can you ensure that your material is superconductor? How would you know that there's no residual resistance? Does anyone know? You don't need to. I can do it on a lab bench if you like. I can measure without any problems. I can show you zero resistance. But no. What's that?
If we can do it, without a superconductor, and
Okay.
know how much is the resistance and compare it.
But well, yes, but there's one way actually. Have you ever heard 4-wire measurement? And it's not like a magic. It's not rocket science. what you do is, it's a clever arrangement. Actually, it's an arrangement that you apply to pretty much any materials. If you don't want to measure resistances of the cables and resistances of the contacts, because we have seen you may have Schottky contacts and they will introduce huge resistance to your sample, but in many cases we don't want. We only want to measure the resistance of the material. So sometimes it's called Kelvin probe as well, unlike the one in AFM. So what you do is you connect an ammeter here, so you measure the amount of current that goes into your system. And let's say you have this superconducting material. And also you put 2 more probes here, and then a voltmeter that's connected to these probes, okay? And what happens is that this current, because of that's created because of the resistances of the wires, will flow through your superconducting material. So your ammeter will read a certain amount of current. And then the voltmeter here will read a voltage drop across the leads. But hey, there's no resistance. So delta R between these legs is 0. So there will be no voltage drop that's going to be read by the voltmeter. So if you do the algebra, V over I, this is 0, so you will get 0. Indeed, using this 4-wire geometry, that's how you can show resistivity versus temperature graphs. Because this is so robust that when you have a finite resistance, it goes down and down. And then as soon as the resistance disappears, it will become 0. So that technique, you should keep this in mind if you're ever planning to measure some material and its resistance or resistivity or conductivity, then this is the way to go. You put 4 contacts. From the inner contacts, you measure the voltage drop because of the known applied current. Okay? So this is a sure way of ensuring that you really show that there's zero resistance in your sample.
Yes.
Sure.
Those wires
Mm-hmm.
not have any effects on our voltage.
No, because now these are metals, and these contacts, if you consider a metal, are pretty much at equipotential. Even if you have a tiny current that goes in here, you will have a potential rise. So you have V1 and V2 here, let's say that's the case. But then same current, it will be here and will be here, so you'll have the reverse of the potential drop. So across the leads, no change. Okay. All right, so this was just an experimental side note, but something that you guys should keep in mind. This is applicable to any materials. Now, I'm going to talk about, not at the moment, I'd like to talk about something else, but I will talk about the superconducting devices and their functions and how interesting they can get. But before that, I would like to focus on some other properties of the BCS theory. We started discussing BCS theory, and then we sort of looked at how Cooper pairs form, and there are a few more items in the list that I would like to add regarding the BCS theory. So it turns out that the Meissner effect, I'm not going to show this, but I'm just going to state Meissner effect is a natural outcome of the theory. The reason has something to do with the quantization of the flux that is in the material, but its demonstration, I'm not sure if I should demonstrate or not, but if you solve the equation, it's just going to be too much equations, so I'm very reluctant to do the exercise here. But if you like, you can check it out. But it comes naturally out of the result of the theory. Then another item in the list, I should again write this down. Electron density of orbitals at Fermi level. Let's denote it with D of EF. Of 1 spin, and electron lattice interaction energy U determines the critical temperature Tc. So this is an outcome again of the BCS theory, and the formula, the final form of the formula is something like this. Tc is given by 1.14 theta. This is the it's the Debye temperature. I'll explain what it is. 1 over U times the EF. And Debye temperature is given by H over CS 2K square root of, I cannot read my own writing, let me check from here. Okay, 6 over pi n over v. So this is the speed of sound in the material. This is the volume, this is the number of electrons, density of electrons, Planck's constant, and this is the wave vector. So Debye temperature defines basically the interaction of, how should I say, so the way you derive Debye temperature is, if you see it, it depends. I mean, these are material constants, and size of the material or density of the electrons plays a role here. Speed of sound. So it's a quantity that defines an interaction between electrons and the speed of sound. So how the phonons, if you like, move in the material. So, and that sort of makes sense because this quantity that defines the superconducting transition temperature is a function of how strongly electrons interact with phonons, and also the interaction energy and so on. So this is followed by, in particular, of course, it must be conventional superconductor, and most type 1 superconductors follow this formula. It agrees pretty well with the experimental observations. And one last item that I would like to add is, I should say, magnetic flux through a superconducting ring is quantized. And the effective unit of charge is 2e, since Cooper pairs are formed of 2 electrons. So rather than flux quantum of h over e, we now have h over 2e. That's sort of expected. It's one of the proofs that indeed really we have 2 electrons that are bound together. So they're acting as one, which in the quantization of the flux that goes through a superconducting ring gives such a flux quantization. I'll go into the details of such devices, but that's something that we should keep in mind. Any questions? Yes. No, we have seen magnetic flux quantization in many materials. Like, we didn't discuss a specific material, but in normal metals or in 2D electron gases, we had magnetic flux quantization. But this is a very specific example where you have a superconducting ring, okay, and then you pass magnetic field through here, and you get a quantization of magnetic field that is passing through the ring. Okay, I'll explain the details and we'll discuss. Oops. Yes, exactly. This is, and that's one thing. Like, you can make superconducting quantum interference devices. So it's pretty much the Aharonov-Bohm effect in action. These superconducting quantum interference devices, it's a pair of superconducting rings, or not a pair, but it's a superconducting ring, and when you bring this near to a magnetic field, what happens is that one of the arm gains a phase factor over the other arm, and the detection limit, I cannot remember, but it is so small. Like, you can, I don't want to make up numbers since we are going to discuss, but I think you can go as low as 10 to the minus 8 Teslas. I feel like I'm using 10 to the minus 8 too often these times. I might be mistaken, but you can really detect very, 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 very small magnetic fields, indeed, that are like very small superconducting quantum interference devices. They are so small that they can be attached to the tip of a scanning tunneling microscope. Of course, it's not going to have nanometer range sensitivity, but it's going to have some very high spatial resolution. So people scan the surfaces with superconducting interference devices and try to observe individual like impurity atoms that are on the surface and so on. So it's that sensitive. But we'll discuss such devices. So for now, let's keep it aside. Sure.
When we put our superconductor exposed to the sun, only the surface Cooper pairs react
Yes.
outside.
Because yeah, it will be effectively shielded by the Cooper pairs on the surface. So as soon as you apply a magnetic field, so in a normal diamagnetic material, what happens is that when you apply a magnetic field, electrons will travel in a direction that will create an opposing magnetic field. So the effective magnetic field within the material decreases. For instance, if you apply 60 Teslas to a frog, you can make it levitate. That's one of the experiments that Andre Geim did actually. We can find its videos. So that's levitation because of diamagnetism. If you apply very strong magnetic fields, then the electrons will respond as strongly, and you can oppose that magnetic field to a certain extent. Now, in the case of superconductivity, the electrons feel no resistance to any sorts of scatterers. So their motion will not be hampered by anything. As soon as they feel the magnetic field, as soon as the magnetic field enters the crystal, these Cooper pairs will arbitrarily fastly go around in orbitals to counteract the magnetic field. And this motion stems from this magnetic field, and it's going to be irrelevant of sort of the the strength of the opposition is going to be equal to the applied magnetic field. Okay? So it comes from the fact that these electrons can go around without any resistance.
So, you also identified the person. So, we use diamagnet because of the opposing magnetic field. And then we say that since because of superconducting behavior, with a smaller magnetic field, you can elevate it or still.
Now, there is still a force that you have to overcome, right? The weight of the superconducting magnet itself, superconducting material itself. So I'm not sure about how to calculate the force, but I would think, it's actually probably not that difficult. But of course, obviously, there is a certain magnetic field strength that you need to have in order to create enough levitation force. So I don't think any arbitrary force, any arbitrary magnetic field strength would be able to levitate superconducting materials. Otherwise, every superconducting material would float by themselves because we are living on a giant magnet, the Earth itself. So you still have a certain magnetic field, but I just don't know how to calculate it. Yeah.
I know the calculation, but let's just know like when we have diamagnets, necessarily we have superconducting situation where we apply magnetic field, or no, like we in the like lab, for example, we make the situation to have the superconducting state, for example, bottom of that material, and this guarantees that with a smaller magnetic field, not we can elevate this.
Oh yeah, exactly. So the difference between as I've written here, this is a perfect diamagnet. So it will oppose any magnetic field in equal strength. This is not something that you would have in normal, ordinary diamagnetic materials. Okay. Any other questions? Sure, please ask questions.
Does this Cooper pairs that
Mhm.
locate in the surface, doesn't this scattering point for other Cooper pairs that pass through the I'm thinking about something like a superfluid, so there are some parts that are bound.
So, I don't know the answer. I mean, perhaps I mean, that's similar to formation of vortices, as we'll see especially in type 2 superconductors. The transition from normal conductor to superconductor regime, that in-between regime, you first form vortices. But again, we are talking about only a very small depth of material, only a few nanometers thick skin on the surface. So, but then you're also right in the sense that beyond certain critical magnetic field will destroy the superconducting order. So even if, but I don't think it's interscattering of Cooper pairs. Rather, it's with the magnetic field you provide enough energy to separate this Cooper pair. So you split, basically spin up and spin down electrons. But I'm not sure if we can say that this is like scattering of Cooper pairs, because the way we think is still like fermions, right? You're thinking that two fermions cannot occupy the same state, so they must scatter, but no, they are bosons that are living in the ground state of the system. So the scattering events are either highly suppressed, or we don't even have a scattering amplitude, because the scattering criteria is not satisfied. Okay. Any other questions? Mm-hmm. 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 Could be. Yeah. Okay. Anything else? So now the energy gaps in superconductors. Again, I'm going to write this down from the book. Superconducting gap is the energy difference between the ground state of the superconductor and the energy of the lowest quasi-particle excitation. Okay, so what we get from the BCS theory is something like this. The energy gap is roughly given by 7.5 kb Tc. So this is the superconducting temperature. One thing that I forgot to mention while our discussion in here is that this electron lattice interaction energy, if it is large at high temperatures, or if it is large at any temperature, then this leads to a larger resistivity when the material is in its normal state. But ironically, when you have large U, then this exponential factor will be lower. Thus, this factor will be higher, so you'll have higher Tc. So the more resistive or the worse metal you have will have the higher TC, so it will become superconducting sooner. That's sort of ironic. So it lives its normal life as a resistive material and then it becomes superconducting sooner. So I'm not sure if it has anything to do with not observing superconductivity in good metals, good conductors like copper, silver, gold. We don't observe superconductivity in these materials, and they are the best conductors we know, so they have very low rho, so which sort of indicates that this U interaction between the electron and lattice is relatively smaller compared to the other metals. So probably one of the reasons why we don't see superconductivity in these materials is that strength of that energy. So there are several methods to actually measure this gap. And my favorite one is this. You take a superconducting material, and then either you take an STM tip, scanning tunneling microscope tip, or you can place an insulator on top of the superconductor, like, I mean, it can be a very thin insulator of a few nanometers. It can be hexagonal boron nitride, or I don't know, anything, any insulating barrier. It can be a very thin layer of Al2O3 if your superconductor is, for instance, aluminum. That's a convenient choice. And then what you do is you put two contacts here and then another contact on top. Of course, this is when you have an insulating material, not the case for STM. Perhaps I should draw, in the STM case, you don't have this red insulating layer in between, okay? And what you do is you measure the current that flows through this contact. So this is a tunneling barrier. And you look at the differential conductance versus the bias you apply between the tip of STM or from this contact to the ground. So either you have a bias like this, so you apply bias between the STM tip and the superconductor, or to this contact pad that's on top of the insulator and the material. And what you get, so at zero bias, the conductance diminishes because there are no available states. And then at certain bias, this is sort of a behavior you get. So as soon as you go beyond this regime, the differential conductance assumes a certain value, okay? And this difference, I don't know, it depends on material to material, but typically the order we are looking at is like, I don't know, minus 0.3 millivolt to plus 3 millivolt. And this gap would be a 0.6 millivolt gap, for instance. So that you can find out the superconducting gap. So with that, let's conclude this lecture, and then on Friday I'll do a very light wrap-up of the topics that we have discussed, and then in the evening we'll have the midterm. Yeah, that's what I'm going to do. That's what I tried to say. I'll do a very light review of what we have done so far. Okay. All right. See you on Friday. Just a second. Yeah. This is Microsoft Whiteboard. Yeah, I mean, well, it came loaded with this. This is much better because in OneNote, when you erase something, it erases in chunks. And also when you try to write it like this, it shows word by word. So once you finish writing something, or letter by letter, I should say, it pops up. That's obviously not ideal, but this is much better.